Greetings and welcome to Friday's lecture. Hopefully you've been reading in the chapter and you're getting this stuff down pretty good in terms of thermodynamics. Today, let's see here, let's go right from the very beginning. Today we're going to talk about Hess's law. And that is just the very next section. Basically, you're responsible for all of Chapter 5. As I mentioned, this is going to be a book test. So what we're going to do is, and I'll give you guys time to hit the pause and get ready for this, get your book and open to page 205 and get this packet if you have it. If you don't, no big deal. You can do this in your notes, but we are going to actually, our notes are going to be doing selected problems from that section, both black and red problems. So we'll do these together because they're a little more involved. So go get those materials if you don't have them already. Otherwise, here we go. So we're on page 205. And you can see we're going to start with problem 5.60a. All right, so let's see what we're talking about here. We've got A going to B, and then B going to C. You should think of this in terms of kinetics as B being a reaction intermediate. Sometimes it's just two separate processes that are easy to tell. Sometimes that happens instantaneously. But let's say it's really, really hard to figure out the energy of A to C, but you can break up and figure out the energy of A to B and B to C. So that's kind of what this is getting to. Now it says use Hess's law to calculate the enthalpy change for the reaction. So this first one's kind of overkill. I just used the same template. So in your notes you can just space these out and just use these as lines on your page. But this is just going to be 3 lines that we'll need for this one because A going to B, you can see, is a positive delta H value. That means endothermic, and you'll get that just kind of hammered in your head, an endothermic reaction. We'll have a positive value, and kilojoules is sort of our preferred unit. And then we'll just skip down a line there and say B going to C is 60 kilojoules. Well, what we can see when we look at this, and if you have some colored pencils or colored pens, you might want to grab those. Pause. Welcome back. And you can X out things that are the same, and this is actually going to get pretty complicated when you see the last one that we do. Is whole thing is going to be all full of writing. But this one you can see, if you know what A going to B is and you know what B going to C is, then by additive property you can make the assumption, see if you can guess what that's going to be. You guessed it, 90 kilojoules. All you got to do is add those together. If you know the parts will sum up to give you your overall reaction. And that's in fact what we have here. We have A going to C. And you just broke it up into 2 parts. Now, back to your book. It says B, construct an enthalpy diagram for substances A, B, and C and show how Hess's law applies. All right? So this is the next page on your packet. So you go to the enthalpy diagram for 5.6b. I don't think yours is probably color, unless Dr. Sorman printed them that way for you. Anyway, we're now at 5.6b, and it's just a table that we're going to use to make a graph. And again, some colored markers or crayons might be helpful here so that you can see these lines. But if you just want to darken in that line right there and darken in this one, this graph will be in increments of 10 kilojoules. So you can see that we go 10, 20, 30, 40, 50, 60, 70, 80, 90. And that was the difference between A and B. And the way that we, between A and C, sorry, the way that we write that is we use arrows to say that going from A to C is an uphill climb, therefore the delta H value being a plus 90 kilojoules. And it's really important that you put in those plus and minus symbols in these problems when you're talking about change in enthalpy. So we know that A to C is plus 90, and to finish off the diagram, we know that A to B was 10, 20, 30, and we know that it was 60 from B to C. So this is how one does an enthalpy diagram for the Hess's law that we talked about. And I like that your book starts out on this simple example because it just hits you right in the face here that you go from 30 to 60, add those two. These are additive head to tail. Going to give you your value of 90 degrees. And just to go back and say, in number 5.59 says, why is this a state function? Okay, so a state function means that it is path independent. Doesn't matter how you got there, you still get there. And a change in enthalpy is a state function. As you will see, A to C, you're still up here, right? On top of the mountain. Here, this guy stopped at a rest area, had a sandwich and a large Dr. Pepper, and then finished the trip. Guess what? These two are both in the same final destination. They took different roads. This guy had a stop. This guy had a non-stop flight. You know, it's kind of like when you're sitting there in the classroom, and you all got there a different way. You came different roads. Some came on Pioneer, some came 58, some came the back Flower Valley Road and took that beautiful drive. But you all ended up in room I-206. So that's what a state function is referring to. So this diagram, I think, is a really good visual. Now, traditionally, you've seen these diagrams as starting here and going up the little loop and the activation energy and coming down. This is kind of a newer way that they're starting to say this is more realistic in terms of what the energy that's happening. So you can also do an enthalpy diagram as a little bump with the activation energy and end up higher or lower depending on the reaction. Okay, so there are different ways to do that, but this is the way that we prefer an enthalpy diagram for this. Okay, so now let's go ahead and take a look at 5.61. So hit the pause and read that question. And they give you a reaction, and they give you the paths, kind of the AB and BC pathways. So this is my final reaction down here. I want to end up with P4O6 solid plus 2 oxygen. And by the way, include these gas and solid symbols. I know on the exam we said you could leave those out, but just include those. Those are going to be important parts of understanding, you know, how these reactions are working. So, so what we're going to do is we're going to, this data was given to us. So go ahead and write that one in the top. And it was also given the fact that this is a very exothermic reaction, nice negative value for the kilojoules. And we need to get this reaction so that it becomes this reaction. So one of the things you'll note is you're like, hey, there's P4O6, there is no P4O10, and the oxygens are over here on the left side, but don't get too bent out of shape about that. Hopefully this will work out that, like, okay, the oxygens are on the left, but I need P4O6. So if you look at your other reaction on the page here, P4O6 is only in one place, and I need to have it on the left side. So, because you can only find it in one place and it has to be on the left side, that means I have to use this reaction in order to figure out Hess's law. So what I did is I just flipped everything around. So guess what this value is going to be? If this process is exothermic, then opposite in magnitude, it's a state function. So the magnitude is exactly the same. You're just going in a different direction. Okay? You're going from Florida to Minnesota at the end of the trip, and you're sad. Okay? So it's the opposite direction. So you flip the sign on this. So that is now something that we're going to be able to apply eventually. Now, on these, I'll crumple up. I thought this was kind of a cool effect. Just crumple up the paper here and say, that one is no longer useful to us. You can do that by just a light line through there, or you can leave it in there if you want as well. I think kind of Xing it out is helpful, especially when you get into the more complicated problems. But don't X it out so that we can't see what's underneath, because that's part of showing your work. So now they gave you this too, P4 plus the 5O2, and you're like, hey, that's how I'm going to end up with some oxygens on the left side. That worked out nice. So you quickly see you don't have to do anything to this. Look at that's P4O10, one of them solid, that's what you got. This is P4O6, and it will cancel out. It'll be left over from that first one right there. And then if you look closely, I've got 5 oxygens on the left and 3 oxygens on the right. So 3 of these guys are going to cancel out. So that's what you want to represent. So if you want to take that color pencil out again and X off what's on the left side, X off the P4s because they're not in this equation and they cancel each other out. Boy, that worked slick. And then the oxygens, all 3 of these guys are gone, and I'm going to cross off that 5, and if I 3 oxygens canceled with 5 oxygens, that of course will leave, you guessed it, 2 oxygens, which is exactly what you need. And one other thing I like to do on this is just kind of circle the things that are left over. You X'd out these guys, and you certainly X'd out that whole thing, so you know you're not. And now I've got this on the left side of the arrow. I've got this on the left side of the arrow. Perfect. And I've got that on the right side of the arrow. So now, then these 2 numbers become additive. And you can see this one's a little bit more negative. So when you add those 2 numbers together, you end up with negative 13,000.0 kilojoules. All right? So that's Hess's law with a pretty straightforward one. On the next lecture, we're going to do some tougher ones. So I will see you on the next lecture.